The ground beneath Nevada is tearing apart. Right now, 2.5 million people live directly above a fault system so dangerous that scientists say it could one day replace the San Andreas entirely. Nevada ranks third in the entire country for earthquake activity, and most people have no idea. We're going to cover the fault lines running under downtown Reno, the soil beneath Las Vegas that turns shaking into something far worse, and the history of quakes that drop the ground 20 feet in a single second. If you enjoy this journey, subscribe and leave a like. Prepare yourselves. We begin. Stand anywhere in Nevada and the ground feels solid. It feels permanent. It feels like it has always been there and always will be. That feeling is wrong. Right now, at this exact moment, the state of Nevada is being pulled apart from the inside. The crust beneath your feet is stretching in two directions at once, like a piece of taffy being pulled slowly by two people walking away from each other. It has been doing this for 20 million years, and it is not stopping. Most people think of earthquakes as random violent events. A fault slips, the ground shakes, then it is over. But in Nevada, the shaking is a symptom of something much larger. The entire western United States is under a slow, constant tearing force, and Nevada sits at the middle of it. The crust here is being stretched so far apart that the landscape has physically transformed. What was once flat and featureless has fractured into hundreds of long valleys and sharp mountain ridges, each one a scar left behind by the earth pulling itself open. Scientists call this region the Basin and Range Province. It covers most of Nevada and large parts of neighboring states. The name describes exactly what you see when you fly over it. Basin, range, basin, range. A rippling pattern of valleys and peaks that stretches for hundreds of miles in every direction. Each one of those valleys is a place where the crust dropped. Each ridge is where the crust held firm. Together they tell the story of a landscape in the middle of a very slow but very real collapse. Here is a number that makes this real. The distance between Reno, Nevada and Salt Lake City, Utah is roughly 520 miles today. 20 million years ago, that same distance was only about 260 miles. The crust between those two cities has stretched to twice its original width. If you drove from one to the other at highway speed and somehow travelled back in time, you would run out of road halfway through. That stretching does not happen smoothly. The crust does not flex like rubber. It is rock, and rock does not bend. It holds and holds and holds, and then it snaps. Each snap is an earthquake, and because the stretching never stops, the snapping never stops either. Nevada experiences roughly 15,000 small earthquakes every single year. Most of them are too small to feel. They happen deep underground while people sleep, while people eat lunch, while kids sit in school. The ground trembles constantly and almost no one notices, but the energy never disappears. It moves through the rock, transferring from one fault to the next, building pressure in places that have been quiet for decades. This is what makes Nevada different from almost every other state. The danger here is not one single fault waiting to go off. The danger is a system, a vast interconnected web of cracks running beneath cities, beneath highways, beneath homes, a web that is under constant stress and has been for millions of years. And something has been changing recently. The earthquakes are getting louder, the swarms are getting bigger. Geologists watching their monitoring screens in the spring of 2026 started seeing patterns that made them lean closer to their computers. Something was waking up in the Nevada desert, and it was pointed directly at the most populated parts of the state. Ask most people which states have the worst earthquakes in America and you will hear the same two answers: California, Alaska. That is the list. And both of those answers are fair. California has the San Andreas Fault. Alaska has some of the most powerful quakes ever recorded on the planet. But there is a third state sitting right between those two reputations, absorbing earthquakes constantly, and somehow staying almost invisible in the national conversation. Nevada is the third most seismically active state in the entire United States. Third out of 50 states, and the vast majority of Americans have no idea. The reason is partly geography and partly timing. Nevada's population clusters around a few cities while enormous stretches of desert sit empty between them. When an earthquake strikes a remote patch of desert outside a town of 2,000 people, the story barely registers. There is no dramatic video of skyscrapers swaying. There is no news helicopter circling a collapsed overpass. There is a gas station with a cracked wall and a few nervous ranchers checking on their livestock. California's earthquakes hit dense cities and generate enormous footage. Nevada's earthquakes have been quietly tearing through the desert for over a century and generating almost no attention at all. That invisibility has created a false sense of safety for millions of people who moved to the state, without understanding what was under them. The numbers tell a story that most Nevada residents have never heard. On average, the state experiences a magnitude 6 or greater earthquake once every 10 years. A magnitude 7 or greater once every 27 years. A magnitude 6 earthquake carries roughly 32 times the energy of a magnitude 5. It can collapse unreinforced buildings, it can sever gas lines, it can knock out power grids. It is the kind of earthquake that makes national news when it hits a city, and Nevada is statistically overdue for one. The invisibility problem runs even deeper when you look at the fault lines themselves. Unlike the San Andreas, which scientists have studied and mapped in enormous detail for over a century, many of Nevada's faults are partially or completely hidden underground. Deep layers of sediment dumped into the valleys over thousands of years have buried entire faults from view. Researchers discover new ones regularly, and each new discovery means a community somewhere just learned it is sitting on something dangerous it did not know existed. That gap between the real risk and public awareness is where lives get lost. People choose homes without asking about fault lines. City planners approve developments without full seismic surveys. Buildings go up using construction standards designed for places with far less risk. Meanwhile, the ground beneath Nevada keeps moving. Every year, the slow-stretching force that has been pulling the state apart continues to load stress onto hundreds of faults simultaneously. Every fault has a breaking point. And a state that experiences 15,000 earthquakes per year is a state where breaking points are being tested constantly. The San Andreas gets documentaries, warning systems, and decades of detailed research. Nevada gets overlooked. And while the world looks the other way, the crust beneath 2.5 million people keeps pulling apart at the seams. The system responsible for most of that tension has a name. And once you understand what it is, the situation starts to feel significantly more serious. Picture a car windshield after a rock hits it at highway speed. The point of impact shatters, cracks spread outward in every direction. No single clean break, just a spiderweb of fractures spreading across the glass, each one connected to the others, each one capable of spreading further with the next bump in the road. That is exactly what the crust beneath Nevada looks like. Geologists call it the Basin and Range Province, but the visual is the cracked windshield. Under California, the crust is being squeezed and ground sideways along a relatively small number of major faults. In Nevada, the crust is being pulled apart. That changes everything about how the rock breaks. Instead of cracking along one or two dominant lines, it fractures across hundreds of faults, all running roughly parallel, all under similar stress, spread across an area the size of several states combined. The Basin and Range Province covers most of Nevada, large portions of Utah and Arizona, and extends down into northern Mexico. It formed because the crust here is being stretched horizontally. As the rock pulls apart, the ground drops in long, narrow strips while neighbouring sections stay elevated. The drops become valleys, called basins. The elevated sections become mountain ranges. Stand anywhere in Nevada and look at the horizon. You are looking at the evidence of 20 million years of the crust ripping itself open in slow motion. The stretching is active, meaning it is happening right now, today, as you listen to this. The crust beneath Nevada is thinner than it was a million years ago. As it thins, it becomes more unstable. Faults that have been dormant for thousands of years can reactivate. Pressure that builds on one side of the state can travel through the rock and trigger something on the other side entirely. This connectivity is the part that unnerves geologists most. in a system of hundreds of interconnected faults, all under constant stress. Predicting where the next major rupture occurs becomes nearly impossible. Scientists can identify the highest risk zones, they can calculate probabilities, but they cannot point at a map and say with certainty which fault breaks next and when. The crust beneath Nevada also varies dramatically in thickness from place to place. Under some mountain ranges, it reaches down nearly 25 miles before hitting the hotter, more flexible rock beneath. Under some valleys, it thins to fewer than 15 miles. That variation creates spots where the crust is especially vulnerable, places where a small increase in stress tips a fault past its breaking point faster than the surrounding rock. Researchers mapping the crust use networks of seismometers, satellites, and ground-based sensors to track even tiny movements in real time. The data they collect looks like a constantly shifting puzzle. Faults creep millimeters. Others lock tight and store energy for decades. The cracked windshield does not sit still. Every small earthquake reshuffles the stress across the entire network. And at the western edge of this massive fractured zone, one particular feature stands out above all the rest. A corridor 600 miles long running along the border between Nevada and California, absorbing a staggering share of the tectonic forces grinding through the region. It has been sitting there, quietly building pressure, for millions of years. And scientists are only now starting to understand just how dangerous it really is. Every year, Nevada gets bigger, not because of new construction or expanding city limits. The state physically grows because the ground itself is spreading apart. Tectonic stretching adds roughly 2 acres of new land to Nevada every single year. 2 acres, the size of about 2 football fields, appearing out of nowhere, created entirely by the crust pulling open. That number sounds almost harmless. 2 acres per year feels slow, it feels gradual, but scale it back 20 million years and the transformation becomes staggering. The land that is now Nevada was once compressed into roughly half the space it occupies today. The entire western interior of the continent has been stretching outward at a pace that, over geological time, reshapes everything. The most concrete way to feel this is the distance between 2 cities. Reno, Nevada sits on the western side of the state. Salt Lake City, Utah sits on the eastern side. Today, driving between them covers about 520 miles. That drive covers ground that 20 million years ago measured closer to 260 miles across. The crust between those 2 cities has doubled in width. If you drove that same route in a time machine set 20 million years in the past, you would slam into the Rocky Mountains before you ever reached your destination. The stretching does not happen in one clean pull. It happens across hundreds of individual faults, each one slipping in tiny increments over thousands of years. The result is the rippling landscape Nevada is known for. Every valley is a place where the crust dropped as the land pulled apart. Every mountain range is the section that stayed high, while the valleys on either side sank. That alternating pattern repeats over and over across the entire state, creating a terrain that from the air looks like a giant washboard. This landscape has consequences for anyone living in it. The valleys that humans naturally settle in, the flat ground where cities grow and roads run, those are exactly the places where the crust has dropped along fault lines. Reno sits in one of those drop zones. Las Vegas sits in another. Carson City sits in another. The cities of Nevada were built on the floors of ancient rift valleys, which means they were built directly on top of the faults that created those valleys in the first place. The faults beneath Nevada valleys are not ancient and dead. Many of them are active. Some of them have ruptured within the last few thousand years. A few thousand years is barely a heartbeat in geological time. A fault that last slipped 3,000 years ago can slip again tomorrow, and by geological standards that makes it a young and active threat. Geologists measure the spreading rate along different parts of the Nevada crust using satellites precise enough to detect movements smaller than the width of a human hair. Year after year, the data shows the same thing. The crust is still stretching, the faults are still loading, the energy is still building. 2 acres per year sounds quiet. But beneath those 2 acres, something enormous is in motion. And sitting right along the most active edge of all this spreading is a feature so large and so powerful that scientists have started calling it the future of the entire Western Plate boundary. On a standard map, the Nevada-California border looks like a clean political line, a straight edge drawn by surveyors, but beneath the surface, that border region is anything but clean. Running along and through it is one of the most geologically significant fault systems in North America, and most people have never heard of it. Scientists call it the Walker Lane. It is a zone of fractures, faults and broken crust stretching roughly 625 miles from Southern California all the way up to Oregon. Picture it as a wide belt of cracked and shifting rock, anywhere from 50 to 100 miles wide, running the full length of the Nevada-California line and then some. The Walker Lane does not look like a single crack. It is more like the aftermath of a tremendous force being applied to brittle rock over millions of years. Hundreds of individual fault segments run through it, some parallel to each other, some at angles, some cutting across others. From the air, the terrain it has created looks chaotic. Sharp mountain ranges interrupted by sudden valleys, dry lake beds sitting in the middle of nowhere, ancient volcanic features poking through the desert floor. All of it is the surface expression of a zone that has been under enormous tectonic stress for a very long time. For most of the 20th century, geologists focused their attention on the San Andreas Fault, and for good reason. The San Andreas is a clear, mappable, dramatic feature running through one of the most populated regions on Earth. It generates enormous earthquakes. Cities from San Francisco to Los Angeles sit close to it. It demands attention. The Walker Lane was treated as a secondary player. A footnote. A collection of smaller faults that contributed to the regional geology but did not rise to the level of the San Andreas. That view has been changing rapidly. Over the last few decades, scientists using satellites, global positioning system networks, and advanced ground sensors have measured exactly how much tectonic motion the Walker Lane absorbs. The answer changed everything. The Walker Lane is currently soaking up roughly 1/4 of all the grinding force between the Pacific Plate and the North American Plate. 1/4 of the total tectonic energy driving the most earthquake-prone region of the continental United States. That is enormous. To put it another way, if you added up all the tectonic force moving through Nevada's fault systems and compared it to what moves through the San Andreas, Nevada's Walker Lane is carrying 1/4 of the combined load. Every year, year after year, that force gets redistributed across hundreds of faults, loading them, stressing them, and eventually breaking them. And the Walker Lane is not stable or static, it is growing. The zone of active faulting is expanding both northward and eastward over geological time. New faults are forming at its edges. Old faults are reactivating as the stress pattern shifts. The system is alive in the most geological sense of that word. At the core of the Walker Lane are several major fault segments that have produced some of the largest earthquakes in Nevada history. Others have not ruptured in recorded memory, but carry enough stored energy to produce events that would rank among the worst natural disasters in American history. And the cities sitting closest to those unruptured faults are not small towns in the desert. Tectonic plates are enormous. The Pacific Plate alone covers roughly 1/5 of the entire surface of the Earth. It is moving. Right now. Every year it creeps several inches in a direction that carries it toward and partly past the North American Plate. That motion generates force on a scale that is genuinely hard to put into human terms. Think of 2 semi-trucks, each weighing 80,000 pounds, grinding side by side at full speed. Now imagine that collision happening along a boundary 2,000 miles long, every second of every day, for millions of years. The force involved does not disappear. It gets absorbed, it gets stored in rock, and eventually it gets released in earthquakes. The primary release valve for this force along the western United States has always been considered the San Andreas Fault. The San Andreas is the official boundary between the Pacific and North American plates. It runs through California like a long, deep wound in the earth, and it has produced catastrophic earthquakes throughout history. The 1906 San Francisco earthquake, the 1989 Loma Prieta event, the 1994 Northridge disaster. But plate boundaries are not always clean lines. The grinding force between two massive plates does not stay politely inside one fault. It spreads. It bleeds into nearby rock. And in the case of the Pacific and North American plates, a significant portion of that grinding force has been bleeding eastward into Nevada for millions of years. Scientists now calculate that the Walker Lane absorbs roughly 25% of the total relative motion between the two plates. 1 in every 4 units of force that drives the San Andreas is also driving the Walker Lane. That 25% gets distributed across the hundreds of faults scattered throughout the system, loading each one at different rates depending on its orientation, depth, and history. The implications are significant. Each major fault in the Walker Lane is accumulating stress the same way the San Andreas does. The timescales differ, the sizes of the resulting earthquakes differ, but the mechanism is identical. Energy stores in rock. Rock holds until it cannot. Then it releases everything at once. Because the Walker Lane is a zone rather than a line, the energy release is less predictable. The San Andreas is a single fault system. Scientists know roughly where it runs, roughly how much stress it holds, roughly when it last ruptured along each segment. The Walker Lane is a network of hundreds of fault segments, many of them poorly mapped, some of them completely unknown until they suddenly move. What makes this especially unsettling is the pace of change. The Walker Lane is absorbing slightly more tectonic motion now than it did a million years ago. As the San Andreas fault locks and becomes harder to move in certain sections, the stress it cannot release gets pushed elsewhere. Some of it travels into Nevada. The Walker Lane is gradually inheriting a larger share of the planetary workload. This is not a slow fade into irrelevance. This is a system quietly growing more dangerous over geological time, loading faults that sit directly beneath some of the fastest growing cities in the American West. And when you understand what scientists now believe the Walker Lane is ultimately becoming, the stakes shift from serious to staggering. The San Andreas Fault is one of the most studied geological features on the planet. Scientists have drilled into it, mapped every inch of it, modelled its behaviour across thousands of scenarios. It runs roughly 800 miles through California and defines where two of Earth's largest tectonic plates meet. Every major California earthquake in the last 100 years connects back to it in some way. And according to a growing number of geologists, the San Andreas is slowly dying. Tectonic plate boundaries do not stay fixed forever. Over millions of years they migrate, split, and reorganize as the forces driving them shift. The San Andreas formed roughly 25 million years ago and has served as the primary boundary between the Pacific and North American plates ever since. But boundaries are only stable as long as the geometry of the plates keeps them in their preferred configuration. That geometry is changing. The bend in the San Andreas near Los Angeles, a region called the Big Bend, creates enormous resistance. The plates have to grind against each other through a curved section where the geometry works against smooth motion. That resistance is forcing tectonic energy to find alternate paths. One of those alternate paths is the Walker Lane. Scientists studying plate motion over geological timescales have identified a pattern. Millions of years ago, the Walker Lane was relatively inactive. As the San Andreas has become increasingly locked in difficult geometry, the Walker Lane has absorbed more of the motion. The trend suggests that this process will continue. The projection that comes from this data is one of the most dramatic in modern geology. Over the next 7 to 8 million years, the Walker Lane is expected to gradually take over as the primary boundary between the Pacific and North American plates. The San Andreas will become less active, the Walker Lane will become more active, the centre of the plate boundary will shift eastward, into Nevada. The physical consequence of that shift is something that sounds impossible. Western California, the strip of land west of the Walker Lane including Los Angeles, San Diego, and parts of the coast, would eventually separate from the rest of North America. The ocean would flood the trough created by the Walker Lane. California would not fall into the sea in a sudden catastrophe. Over millions of years, it would gradually become an island, drifting northward along the coast. This process is far beyond any human timescale. 7 million years from now, the species that calls itself human may be something unrecognizable or entirely gone. The details of what the coast looks like in 7 million years matter less than what this migration tells us about the Walker Lane right now. A fault system that is growing in power, a system that is absorbing more tectonic energy each geological epoch, a system that has not yet fully expressed the forces being loaded into it. That is what sits beneath Nevada today. And while the continent-splitting future is millions of years away, the earthquakes building inside that system are very much a present-day problem. Scientists watching the Walker Lane in real time have been tracking something that accelerated dramatically in the spring of 2026. 2 acres per year sounds manageable, small even, but every single one of those 2 acres comes with a price. The price is geological violence, paid in the currency of fractured rock and released energy. When the crust stretches, it does not stretch evenly. Rock is rigid. It stores the stretching force the way a compressed spring stores energy. It holds longer. And when it finally releases, it releases all at once along a fault line, sometimes in seconds. Those seconds are what people feel as earthquakes. So the 2 acres per year is not a gentle, continuous growth. It is a running debt. The crust owes its expansion to hundreds of faults that are constantly loading up and occasionally snapping. Each snap repays a small portion of the debt. The debt, however, keeps accumulating because the forces driving the stretching never stop. The Basin and Range Province, which includes all of Nevada, has been running this debt cycle for 20 million years. In that time, the crust has thinned considerably. Under the valleys of Nevada, the crust has stretched and thinned enough that the boundary between the cold, rigid upper rock and the hotter, more flexible rock below sits unusually close to the surface. That closeness means heat from the Earth's interior reaches the surface more easily, which is why Nevada has abundant geothermal activity, hot springs. Geothermal power plants. Volcanic features scattered across the desert. It also means the crust is more vulnerable. Thinner rock under sustained tension fractures more readily than thick, cold, stable rock. Faults that might stay locked for centuries elsewhere may slip more frequently in Nevada simply because the mechanical conditions favour movement. The 2 acre per year growth rate averages out something that is actually very uneven in practice. Some years the faults are quiet, the crust stores energy without releasing it. Other years, a sequence of earthquakes releases energy faster. The ground literally drops in places, opens in others, and the landscape reshapes itself in the span of hours or days. In 1954, a sequence of earthquakes in central Nevada dropped patches of ground by up to 20 feet in under a minute. 20 feet. That is roughly the height of a 2-story house. A section of land that had been at one elevation for thousands of years dropped instantly to a new level. Fences crossing the fault line ended up with one side standing 6 feet higher than the other. Roads simply ceased to exist. That kind of sudden vertical movement is an extreme case, but it illustrates what the slow debt of stretching looks like when it comes due all at once. The 2 acres that Nevada gains every year represent small, continuous entries in a ledger. The earthquakes are the payments, and the ledger is far from balanced. Researchers tracking ground movement with satellites can now see individual faults creeping at different rates across the state. Some slip a fraction of an inch per year in quiet, steady motion. Others are completely locked, storing decades or centuries of energy without moving at all. Those locked faults are the ones that concern scientists most. A locked fault is a pressurized system waiting for its moment. And in the spring of 2026, one of those moments arrived in a patch of northern Nevada desert that had been quiet for years. The morning of April 13th, 2026 started like any other morning in Silver Springs, Nevada, a rural community of a few thousand people sitting in the high desert about 30 miles east of Carson City. The landscape there is wide and open, dry mountains in the distance, a few gas stations, ranch homes spread across the valley floor, the kind of place where you can hear wind and almost nothing else. At 4:53 in the morning, that silence ended. A magnitude 5.7 earthquake ruptured a fault segment approximately 12 miles from the center of Silver Springs. The rupture happened fast, the way all earthquake ruptures do. Stored energy released along a fault plane in seconds. The ground directly above lurched, dropped, and shook violently. People were thrown from beds, items flew off shelves. A section of the fault visible at the surface showed fresh cracking, the Earth's surface torn open along a line that had been invisible the day before. Magnitude 5.7 is genuinely dangerous in populated areas. It carries roughly the same energy as several nuclear weapons detonating simultaneously underground. Buildings with weak foundations can crack or collapse. Chimneys fall, gas lines rupture. And this earthquake was shallow, meaning it originated close to the surface, which sent maximum energy upward into everything standing on the ground above. The shaking was felt 400 miles away. That is roughly the distance from New York City to Boston and back combined, except in a single direction. People in Reno felt it. People in Sacramento, California felt it. Reports came in from hikers in the Sierra Nevada mountains who felt the ground move through their boots on rocky trails. In Silver Springs itself, the damage was immediate and visible. Local businesses suffered cracked walls and broken windows. Heavy cast iron objects in kitchens and garages were thrown across rooms. At one grocery store, entire aisles collapsed, sending cans rolling across cracked tile floors. The structural damage was not catastrophic by the standards of a truly massive earthquake, but the community was shaken in every sense of the word. Emergency services mobilized quickly. Geologists from the University of Nevada arrived within hours to assess the damage and set up additional monitoring equipment. The Nevada Seismological Laboratory began tracking the aftershock sequence, and what they saw on their screens was deeply concerning. The fault had not finished. The initial rupture had released pressure along one segment, but the stress it displaced had moved into adjacent rock. Small quakes began appearing on the monitors almost immediately after the main event. Then slightly larger ones. Then clusters. The aftershock sequence was intensifying rather than calming down, which told researchers that the fault system in this area was more active and more stressed than anyone had mapped. Within the first 24 hours, dozens of aftershocks had rattled the region. Within the first week, hundreds. But the sequence was only getting started, and what came next surprised even the scientists who had been watching Nevada's crust for decades. After a major earthquake, the physics of what happens next follows a general pattern. The main shock releases the largest amount of energy. Aftershocks follow, each one smaller than the last, gradually decreasing in frequency and strength over days, weeks, or months. Scientists call this Omori's Law, named after the Japanese researcher who first described it over a century ago. The sequence decays. The ground settles. Life slowly returns to normal. Silver Springs did not follow that pattern. In the weeks after the April 13th main shock, the region experienced over 200 additional earthquakes. That number alone is significant. But the specific shape of the sequence is what caught researchers off guard. A magnitude 4.8 struck the same area weeks after the initial event. Then a magnitude 5.2 hit, again in almost the exact same location as the original rupture. These were large aftershocks, strong enough to cause additional damage, strong enough to be felt across the region, strong enough to suggest that the fault had stored more energy than the initial rupture had released. In earthquake science, when a fault keeps producing significant earthquakes after the main shock, it raises an uncomfortable question. Which earthquake is actually the main shock? In some historical sequences, what initially appeared to be the main shock turned out to be a foreshock, an event that preceded a much larger rupture. Scientists cannot determine this in real time. Only after the sequence ends can they look back at the data and classify what happened. The Silver Spring sequence kept geologists closely watching their instruments. Every new significant aftershock reset the clock on the danger window. Standard practice after a major earthquake is to calculate the probability of a larger event occurring within the next several days. Each time a magnitude 4 or 5 aftershock struck, that probability window reset. Meanwhile, the people of Silver Springs were living through the sequence in real time. Aftershocks rattled homes at 2 a.m. and again at noon. Cracks that had been repaired opened again. Families who had started returning to their damaged properties found fresh damage waiting for them. Sleep became difficult. Anxiety became constant. The psychological toll of living on ground that will not stop moving is something earthquake scientists document in every major sequence, and Silver Springs was no exception. The economic damage accumulated quickly. Small businesses that had started cleanup operations found new damage from subsequent shocks. Insurance claims piled up. Roads developed new cracks. Water lines in older sections of the community began showing stress fractures that had to be located and repaired. For geologists, the sequence revealed something important about the fault structure beneath this part of Nevada. The multiple large aftershocks suggested a fault network with multiple loaded segments close together. When the initial rupture transferred stress to neighbouring segments, several of those segments were already close to their own breaking points. The system was primed. That kind of primed, multi-segment fault network is exactly what scientists worry about most. Individual faults can produce damaging earthquakes, but fault networks where multiple segments can fail in sequence, each one transferring stress to the next, those are capable of producing something much worse. And the Silver Spring sequence was happening in the relatively unpopulated northern Nevada desert. The fault systems running directly beneath Nevada's cities carry far more stored energy and far more people sitting above them. 400 miles. Repeat that number for a moment. The Silver Springs earthquake on April 13th, 2026, generated shaking strong enough to be felt 400 miles from its epicenter. That is roughly the distance from Chicago to Detroit and then all the way back to Chicago again, laid out in a single straight line. For a magnitude 5.7 earthquake, that distance is remarkable. Most earthquakes of that size are felt within a radius of perhaps 100 miles. The shaking typically decays quickly as the seismic waves travel through rock, losing energy with distance. For Silver Springs to produce perceptible shaking at 400 miles, something about the local geology had to be working in the earthquake's favour. 2 factors explain it. The first is depth. The Silver Springs earthquake was a shallow event, meaning the fault rupture started close to the surface rather than deep underground. Shallow earthquakes send their energy more directly upward into the ground above them, and they also send surface waves outward with more strength than deeper events. The shaking at the source was more violent than it would have been for a deeper quake of the same magnitude. The second factor is the rock itself. Much of the western interior of the United States is underlain by ancient, cold, dense rock that transmits seismic waves efficiently, like a bowling ball rolling across a hardwood floor rather than a carpeted one. Seismic waves travelling through this type of rock lose less energy per mile than waves travelling through softer, more fractured material. The result is that earthquakes in the interior west often travel farther than earthquakes of the same size along the California coast, where softer and more fractured rock absorbs energy faster. Reports came in from hikers in the Sierra Nevada mountains, about 60 miles to the west. People in Sacramento, California described a sudden dizziness and the sound of their windows rattling. In Reno, located about 50 miles to the northwest, many residents felt what they described as a slow rolling sensation followed by sharper shaking. The Nevada Seismological Laboratory received hundreds of felt reports within the first hour. The 400-mile reach of the Silver Springs quake is a reminder that earthquakes do not respect political boundaries or city limits. A fault in the middle of Nevada desert affects people in California, Utah, and beyond. And it raises an obvious question. If a magnitude 5.7 in a rural area can reach 400 miles, what does the shaking radius look like for a magnitude 7 that strikes closer to an urban centre? Scientists run these calculations regularly. The models are sobering. A magnitude 7 earthquake centred near downtown Reno would produce violent shaking throughout the city, strong shaking across the Lake Tahoe region, and moderate shaking across a substantial portion of Northern California. The energy involved is roughly 1,000 times greater than what Silver Springs released in April. Reno is not in some distant, isolated desert. It is a city of over 250,000 people, surrounded by suburbs and connected to major infrastructure including highways, airports, and water systems. The fault lines running through it have been there for millions of years. They have ruptured before. And the question scientists are now asking is deceptively simple. When does Reno's turn come? Most people imagine fault lines the way they appear in movies. A visible crack in the ground, a seam that runs across the landscape, clearly marking where the danger lies. On one side, safety, on the other, risk. That picture is almost completely wrong. Fault lines beneath cities are invisible. They run through layers of sediment, concrete foundations, underground pipes, and bedrock without announcing themselves. In many cases, the surface directly above a major active fault looks completely normal. A parking lot, a residential street, a school playground. Nothing suggests what is sitting directly underneath. This is the situation in Reno. Active fault lines run directly through the city. Several major fault segments slice through the urban core, passing beneath neighborhoods, crossing under major roads, and threading through areas with dense residential and commercial development. Some of these faults have been identified through careful geological mapping, others remain poorly understood, and a few may be entirely unknown. The way geologists find buried faults is painstaking work. They drill into the ground and extract core samples that preserve layers of ancient soil and rock. When a fault has ruptured in the past, it leaves evidence in those layers. Soil horizons get offset. Materials that should sit in flat, even layers instead show sudden vertical jumps. Organic material buried in the offset layers can be dated using carbon analysis, giving scientists a rough timeline of when the last major rupture occurred. The problem is coverage. Drilling enough cores to map every fault beneath a city the size of Reno would take decades and enormous funding. What geologists have instead is a partial picture, detailed in some areas and almost blank in others. They know where certain fault segments run. They can estimate their rupture histories. But the gaps in knowledge are real and significant. Buildings constructed over active faults face the worst outcome during a major earthquake. When a fault ruptures beneath a structure, the ground on one side moves relative to the other side. The foundation gets torn in two directions simultaneously. Even the strongest buildings struggle to survive that kind of differential ground movement. Most older buildings, built before modern seismic codes, are extremely vulnerable. Reno has thousands of older structures. Buildings from the mid-20th century that predate comprehensive earthquake engineering. Unreinforced masonry structures, the brick-and-mortar buildings that look solid and permanent but perform catastrophically during strong shaking. Many of these older buildings sit in the exact areas where the known fault segments cross the city. California's experience with this problem is instructive. After the 1994 Northridge earthquake, engineers inspecting the damage found that modern buildings built to code suffered far less than older structures. But California had spent decades building knowledge of its fault network and updating construction standards accordingly. Nevada has not had the same sustained focus, and beneath the quiet streets of Reno, the fault lines that geologists have identified are still far fewer than the total number that almost certainly exist. Every blind fault, every buried segment that has not yet been mapped, represents a gap between what the city is prepared for and what the ground is actually capable of doing. The science of finding those hidden faults is getting better every year, But the faults are not waiting for science to catch up. Reno calls itself the biggest little city in the world. That slogan refers to its outsized personality for a city of its size. But in geological terms, Reno sits in a position that makes the slogan feel unintentionally accurate in a different way. The city packs an enormous seismic risk into a relatively compact area of urban development. The Reno-Carson City Corridor, which includes the cities of Reno, Sparks, Carson City, and the communities of Minden and Gardnerville running along the valley to the south, is home to hundreds of thousands of people. The entire corridor is built on valley floor sediments deposited over thousands of years. Beneath those sediments are active fault systems. Geologists studying this region have identified multiple fault segments running through and around the populated areas. The most concerning of these sit directly beneath or immediately adjacent to downtown Reno. A rupture on one of the major segments close to the city centre would do what geologists call a direct hit. The fault would move. The ground on one side would shift relative to the other, and everything built across that fault line would experience the worst possible kind of earthquake damage. The mathematics of the risk have been published clearly in scientific literature. The Reno-Carson City-Tahoe corridor faces a 60 to 75% probability of experiencing a magnitude 6 or greater earthquake within the next 50 years. That probability range means that on current odds, a significant earthquake striking this corridor within the lifetime of a teenager listening to this is more likely to happen than not. A magnitude 6.0 earthquake carries enough energy to seriously damage unreinforced buildings and cause moderate damage to well-engineered structures. A magnitude 6.5, which is within the realistic range for faults in this system, carries roughly 5 times more energy than a 6.0. The difference between those numbers on the ground is enormous. Reno is not a poorly prepared city by the standards of Nevada's history. Emergency managers have worked to identify vulnerable structures and develop response plans, but the sheer number of older buildings, the incomplete mapping of the fault network beneath the city, and the rate at which the urban population has grown in recent decades have combined to create a gap between the city's preparedness and the actual hazard it faces. Infrastructure is the most vulnerable category. Water mains running across active faults can be severed by fault displacement, cutting off water to the city for days or weeks. Gas lines crossing fault zones can rupture and ignite. Road surfaces can crack and shift, cutting off access for emergency vehicles. Underground electrical systems can fail simultaneously across multiple locations. After a major urban earthquake, the first 72 hours are critical. Emergency services are overwhelmed. Hospitals fill quickly. The ability to move resources around the city depends entirely on which roads remain intact. A fault rupture directly through downtown Reno would cut some of those routes entirely. Reno has resources, planning, and a geologically aware population compared to many cities. But awareness of the risk and full preparedness for it are different things. And 50 miles to the south, in the capital of Nevada, a quieter but equally serious danger runs along the same fault corridor. Probability is a strange thing. Say there is a 10% chance of rain tomorrow, and most people leave their umbrella at home. Say there is a 70% chance, and most people grab it on the way out the door. 70% feels serious. It feels likely. It feels like something you should prepare for. Scientists have calculated that the Reno-Carson City-Tahoe corridor has a 60 to 75% probability of experiencing a magnitude 6 or greater earthquake within the next 50 years. 75%. Higher than the chance of rain that makes you grab your umbrella. That number comes from careful, systematic analysis. Geologists study the fault segments in the region, measure how fast strain is building on them, examine the historical record of past earthquakes, and use established models of earthquake recurrence to calculate probabilities. The 60 to 75% range reflects genuine scientific uncertainty about which specific faults will move and when. But the range does not reflect uncertainty about whether a major earthquake will happen. It reflects uncertainty about the precise timing. To understand what a magnitude 6 or greater earthquake does to an urban area, it helps to look at past events. In 2016, a magnitude 6.2 earthquake struck central Italy, a country with strict building codes and earthquake awareness. 299 people died. Thousands of structures collapsed or were condemned. The economic cost reached billions of dollars. Central Italy's geology and building stock are in some ways comparable to parts of Nevada. In Reno, an earthquake of that magnitude or larger would hit a city with a significant inventory of older structures, many built before modern seismic engineering requirements were established. Brick buildings from the mid-20th century, older residential homes with unreinforced walls, commercial buildings in the historic downtown district with heavy facades and outdated foundations. The economic damage estimates for a major earthquake in the Reno corridor run into the hundreds of millions to billions of dollars. Annual losses from earthquake activity in Nevada are already measured in the tens of millions even without a major event. A single magnitude 6.5 rupture directly beneath the city could generate economic losses that exceed the city's entire annual budget many times over. The 50-year window in that probability calculation matters enormously. 50 years from now, the children born today will be in their 50s. They will be raising families, running businesses, living in homes across the Reno Valley. The probability does not drop off after 50 years. If a major earthquake does not occur within that window, the accumulated stress on the faults continues to grow, making subsequent decades more likely to produce a larger event. This is the uncomfortable reality of living on an active fault system. Time does not make the danger smaller, it makes it bigger. Every year that passes without a major rupture is another year of stored energy sitting in rock beneath cities and neighborhoods. And the Reno corridor, for all its very real risk, may not even be the most vulnerable urban area in Nevada. Further south, in a city far larger and built on ground with its own set of dangerous properties, millions of people are sitting on a different kind of threat entirely. Carson City does not have the profile of Reno or Las Vegas. It is Nevada's capital, a city of roughly 60,000 people sitting in a wide valley at the base of the Sierra Nevada mountains. Quieter than Reno, less crowded, a place where state government workers commute to office buildings and families live in neighborhoods that feel stable and settled. The ground beneath Carson City is not stable. The valley it sits in was created by fault activity. The mountains to the west, the Sierra Nevada range, rose along fault systems as the valley floor dropped. The same faults that built the landscape remain active today. The Carson City area sits on a segment of a fault system that geologists classify as capable of producing major earthquakes. The specific fault segments running through and around Carson City have been studied carefully enough to confirm they have ruptured in the relatively recent geological past, meaning within the last several thousand years. Fault trenching operations, where researchers dig across a fault to examine the layers of earth and find evidence of past ruptures, have revealed clear signs of movement that scientists date to historical times by geological standards. Just south of Carson City, the communities of Minden and Gardnerville occupy the next valley segment. This is the Carson Valley, a flat agricultural area flanked by mountains on both sides. The mountains on either side mark the edges of fault systems. The valley floor is the dropped block sitting between them. Beautiful landscape, genuinely dangerous geology. The eastern Sierra Nevada front fault system, running along the base of the mountains above Carson Valley, is one of the more active fault systems in the region. It has generated significant earthquakes in the geological past and carries enough stored energy to do so again. A rupture along this system would send the strongest shaking directly into the communities sitting at its base. For the residents of Carson City and the Carson Valley, seismic risk combines with another factor that amplifies the danger significantly. The valley floor is covered in water-saturated sediments deposited by ancient lakes and rivers. When strong shaking hits saturated loose sediment, something called liquefaction can occur. the ground momentarily behaves like a liquid. Buildings tilt. Foundations sink unevenly. Underground pipes and cables shift. Roads develop waves and sinkholes. Liquefaction damage is visually dramatic and structurally catastrophic. After a major earthquake in Anchorage, Alaska in 1964, entire neighborhoods built on waterlogged sediments slid into the ocean when the ground liquefied beneath them. Carson Valley sits on similar types of sediment in several areas. The population of the Carson City-Minden-Gardnerville corridor is modest compared to Reno or Las Vegas, but the infrastructure serving this region connects to the rest of Nevada and to California through mountain passes that would be vulnerable to seismic disruption. Highway 50 and Highway 50 the Carson City corridor also houses important state government facilities, the Nevada State Prison, and critical water infrastructure serving both urban and agricultural users. A major earthquake hitting this corridor would not just affect the local population, it would disrupt connections across the region. And it would occur within a fault system that extends directly northward into Reno and southward toward the next major population center. The Reno-Carson City corridor represents one axis of Nevada's seismic risk. The other axis, 400 miles to the south, is built on far softer ground and holds far more people. Las Vegas is one of the most recognizable cities on the planet. The Strip. The casinos. The towers of glass and steel that rise from the desert floor, lit up against the night sky like something from a dream. It feels permanent. It feels engineered to withstand anything. That feeling masks a geological reality that engineers and city planners are only now starting to fully reckon with. Las Vegas sits in a wide desert basin surrounded by mountain ranges on all sides. To most visitors, the flat valley floor looks like the most stable possible ground. No mountains nearby to cause landslides, no coastline to worry about, just flat, open desert. But the valley floor is not a stable platform. It is the dropped block of a rift zone created by fault activity over millions of years. And those faults are still active. The Frenchman Mountain Fault runs along the eastern edge of the Las Vegas Valley, near the community of Henderson. Frenchman Mountain itself is a dramatic rock formation visible from much of the city, a raised mass of ancient stone sitting just outside the urban edge. The fault running along its base has produced large earthquakes in the geological past. Scientists calculate it is capable of producing a magnitude 7 or greater event. A magnitude 7 is enormous. The energy involved is 10 times greater than a magnitude 6. The shaking it produces can level unreinforced buildings over a wide area. The Eglinton Fault runs through the northwestern part of the Las Vegas Valley, cutting through areas that have seen rapid residential development over the last 3 decades. This fault is also capable of producing a magnitude 7 earthquake. Unlike Frenchman Mountain, the Eglinton Fault runs through densely built suburban neighborhoods. Homes, schools, and commercial centers sit directly above and adjacent to its trace. What makes Las Vegas's situation distinct from Reno's is the scale of recent growth. Reno has grown steadily. Las Vegas has exploded. The population of the Las Vegas metropolitan area has grown from roughly 800,000 people in 1990 to over 2 million today. That growth happened fast, and it happened by spreading outward across the valley floor in every direction, including directly over fault zones and onto unstable ground. Zoning regulations in Nevada require seismic studies for major construction projects. But the rapid pace of development, combined with the incomplete mapping of the fault network beneath the valley, means that some structures were approved based on an incomplete picture of what lies beneath them. The Las Vegas metropolitan area has been growing faster than the geological understanding of the ground it is built on. The Frenchman Mountain and Eglinton faults represent the most clearly identified threats, but geological surveys of the Las Vegas basin have identified numerous other fault structures throughout the valley. Some are shorter segments capable of smaller but still damaging earthquakes. Others remain poorly understood. The pattern beneath Las Vegas, like the pattern beneath much of Nevada, is a network of faults in a valley created by those faults. with millions of people living on top. And there is one more factor that makes a Las Vegas earthquake uniquely dangerous. Something about the valley floor itself that transforms ordinary shaking into something far more destructive. Something that has surprised earthquake scientists studying the region, and that will permanently change the way you think about that flat, open desert basin. Stand on solid bedrock during an earthquake and the shaking is bad. Stand on deep, loose sediment during the same earthquake and the shaking is dramatically worse. This is one of the most well-documented and consistently observed phenomena in earthquake science. The type of ground beneath you can amplify seismic waves, stretching out the shaking, making it more intense, and extending how long it lasts. Las Vegas sits in a basin filled with deep layers of sediment. Ancient lakes once covered this valley. Rivers deposited material from the surrounding mountains for thousands of years. The result is a thick accumulation of sand, gravel, silt and clay sitting on top of the underlying bedrock. In some parts of the Las Vegas Valley, these sediment layers extend more than 1,000 feet deep before reaching solid rock. When seismic waves generated by an earthquake enter this sediment, they slow down. As waves slow down, they grow taller, the way an ocean wave grows taller as it enters shallow water near a beach. The energy gets compressed into a slower, taller wave, which translates to stronger ground motion at the surface. Seismologists call this site amplification, and it is the difference between moderate shaking and catastrophic shaking for the same earthquake magnitude. The specific sediments beneath parts of the Las Vegas Valley are particularly efficient at amplifying certain frequencies of seismic waves. Those frequencies happen to match the natural resonance frequencies of multi-story buildings. A building has a resonant frequency, the rate at which it naturally wants to sway back and forth. When earthquake shaking matches that frequency, the building sways more and more with each cycle, the same way a playground swing goes higher if you push it at exactly the right moment. This amplification of building motion on top of the ground amplification created by the sediment produces a compounding effect. Researchers studying this phenomenon in the Las Vegas Valley have compared it to a bowl of jelly. Tap the rim of a bowl of jelly and the jelly shakes and wobbles long after the tap itself has ended. The sediment in the Las Vegas basin behaves similarly. Shaking that would last 10 seconds on nearby bedrock can last 30 or 40 seconds on the valley floor. Those extra seconds matter enormously for buildings which fatigue and fail under repeated cycles of stress. Mexico City in 1985 provided a chilling demonstration of this effect. The earthquake that struck that year originated over 200 miles away on the Pacific coast. Buildings in Mexico City, which sits in an ancient lake bed similar in character to Las Vegas basin sediments, experienced amplified shaking many times stronger than surrounding areas built on rock. Thousands of buildings collapsed. Nearly 10,000 people died. The epicenter was 200 miles away. The sediment did the rest. Las Vegas has never experienced a major earthquake in its modern history. The city's entire high-rise skyline, its dense hotel towers, its thousands of residential buildings, has never been tested by the amplified shaking its geology is capable of producing. Computer models of a magnitude 7 earthquake near Las Vegas produce results that engineers describe with visible concern. The compounding effect of the Frenchman Mountain or Eglinton fault firing beneath sediment-filled valley would be felt in ways that flat maps of the region simply cannot convey. And the buildings built first. The older structures from the 1950s, 60s and 70s that predate modern seismic codes stand directly in the path of forces they were never designed to survive. Las Vegas did not grow slowly. It did not spread carefully outward from a stable core, testing the ground before committing. It exploded. Decade after decade, the city pushed its boundaries outward across the valley floor at a pace that outran geological surveys, outran infrastructure planning, and in some cases outran basic knowledge of what the ground could handle. In 1950, the population of Las Vegas was roughly 24,000 people. By 2000, it had passed 1 million. Today, the metropolitan area holds over 2 million residents and continues to grow. That is one of the fastest sustained urban expansions in American history, and almost all of it happened on the flat valley floor of a seismically active rift basin. The growth moved in every direction, north into the Summerlin development, built on the western valley edge near fault structures, east into Henderson, sitting adjacent to the Frenchman Mountain Fault, south and northwest across the valley floor over the deep sediment layers that scientists know will amplify shaking in a major earthquake. Every new neighbourhood, every new school, every new hospital and shopping centre expanded the city's footprint over ground that carries real seismic risk. Developers were not ignoring geology. Nevada has building codes that require seismic considerations in construction. Modern buildings in Las Vegas are engineered to handle significant shaking. The issue is that modern code-compliant construction represents only a portion of what stands in the city today. Every decade of growth left behind buildings engineered to the standards of that decade, not the standards of today. The city that exists now is a layered accumulation of construction spanning 8 decades, each layer reflecting the earthquake knowledge and requirements of its time. The oldest structures from the 1940s and 50s were built with almost no seismic considerations at all. Buildings from the 60s and 70s incorporated early seismic codes that were far weaker than current requirements. Even structures from the 80s and 90s used standards that have since been updated based on improved understanding of the region's fault network. This creates a patchwork of vulnerability across the city. A modern hospital built last year may be engineered to survive a major earthquake with minimal structural damage. An older apartment building 2 blocks away may be constructed of unreinforced masonry that would fail catastrophically under the same shaking. In a city of 2 million people, the concentration of vulnerable older structures in certain neighbourhoods creates pockets of extreme risk. The rapid growth also created infrastructure challenges that compound the seismic risk. Water mains installed in the 1960s cross-fault zones using older pipe materials not designed to handle fault displacement. Electrical transmission lines follow routes that made geographic sense at the time, but that seismic analysis now identifies as vulnerable. The underground utility network of a rapidly grown city is a system of patches and additions, not a coherent design built with earthquake resilience from the start. Las Vegas also draws millions of visitors. On any given day, the population in the tourist corridor along the Strip is substantially higher than the residential count would suggest. Hotel towers pack thousands of guests into structures of varying ages and seismic designs. A major earthquake striking during peak tourist season would expose an enormous population to its effects. The city that built itself on unstable ground has never faced a true test of what that ground will do. But Nevada's history says the test is coming. The only question the history cannot answer is precisely when. The year was 1915. October 2nd. Most of Nevada was empty desert. The state's population was a fraction of what it is today. Ranchers and miners made up the bulk of the permanent residents. Pleasant Valley, a remote stretch of high desert in central Nevada, was exactly the kind of place where almost no one lived and almost no one paid attention. At 7:30 in the evening, the ground cracked open. A magnitude 7.3 earthquake ruptured along the fault system beneath Pleasant Valley. To understand what that number means in physical terms, a magnitude 7.3 releases energy roughly 1,000 times greater than a magnitude 5.3. The fault moved. The ground on one side lurched relative to the other. A fresh scarp, a visible cliff created by the fault displacement, tore across the desert floor for 37 miles. 37 miles of new crack in the Earth's surface, appearing in seconds. The shaking travelled enormous distances. In Reno, roughly 150 miles to the northwest, people felt the ground move violently enough to interrupt a dance being held in the city. Musicians stopped playing. Guests grabbed walls and door frames. Windows rattled in their frames across the city. The shaking reached San Francisco to the west and Salt Lake City to the east, felt by people hundreds of miles in every direction from the rupture point. In the valley itself, the damage was severe, but the population was so sparse that casualties were limited. The fault scarp that appeared that night is still visible today, more than a century later. You can drive to Pleasant Valley and walk along the edge of that ancient rupture, see where the ground stepped up several feet along a line that stretches almost to the horizon. It is one of the most dramatic surface ruptures preserved in the American West. The Pleasant Valley earthquake carries an important lesson for Nevada today. It struck on a fault that had no recorded history of major activity before 1915. Nobody knew that particular section of the basin and range was capable of a magnitude 7.3 event. The fault simply broke, with no warning that anyone at the time could detect or interpret. It went from an anonymous patch of Nevada desert to a catastrophic rupture point without any advance notice that modern science would have recognized. Geologists studying the Pleasant Valley Fault after the earthquake found evidence that it had ruptured multiple times in the distant geological past. The lack of recorded history before 1915 did not mean the fault was new. It meant the fault was old and had simply been quiet long enough that no human memory captured its previous activity. A quiet fault is often a loading fault. A loading fault eventually breaks. Nevada has many faults with similar histories, long periods of quiet followed by sudden, violent rupture. The geological record shows this pattern repeatedly, and the state's population in 1915 was small enough that even a magnitude 7.3 in a remote valley caused limited casualties. The population sitting on Nevada's fault systems today numbers in the millions. What happened in Pleasant Valley in 1915 was dramatic. What happened in the central Nevada desert 39 years later was something else entirely. Single major earthquakes are terrifying, but a cluster of major earthquakes striking the same region within months of each other is a different category of event entirely. In 1954, central Nevada experienced exactly that. It started in February of that year. A magnitude 6.6 earthquake struck the Fallon area, causing damage to buildings and setting off a wave of concern among geologists monitoring the region. That alone would have been a significant event. But the fault system in the area was not finished. In July, a magnitude 7.0 earthquake struck near Fallon again. The same general region, but a different fault segment, the second major earthquake in 5 months. Then, in August, 2 catastrophic earthquakes hit within 4 minutes of each other. A magnitude 7.1 struck the Fairview Peak area. Before the shaking from that event had fully subsided, a magnitude 6.9 hit the nearby Dixie Valley. 4 minutes. The ground shook continuously as 2 major earthquakes triggered each other in rapid succession. The Dixie Valley and Fairview Peak earthquakes together produced some of the most dramatic surface ruptures in American geological history. Fresh scarps tore across the desert, ground that had been flat dropped or rose by several feet in seconds. Roads crossing the fault zones were torn apart. A major highway was cut clean through by fault displacement, with one lane suddenly sitting several feet higher than the other. This event demonstrated something important about how fault systems behave. When a major earthquake occurs on one fault segment, the stress it releases does not simply disappear. It transfers to neighbouring fault segments, potentially pushing them closer to their own breaking points. The 4-minute gap between the Fairview Peak and Dixie Valley earthquakes suggests that the first rupture triggered the second almost immediately. The faults were so interconnected and so loaded with energy that one failure cascaded into another. For geologists watching Nevada today, the 1954 cluster serves as a model. It shows what the Basin and Range Province is capable of producing when multiple fault segments are simultaneously near their limits. And it raises a serious question about the current state of the Walker Lane system, where decades of accumulated stress are distributed across hundreds of fault segments that geologists know are interconnected. The 1954 earthquake struck in areas where the total population was extremely small. Central Nevada in that era held scattered ranches, a few small towns, and military installations. The affected region today looks largely similar. Sparse, remote, low population. The fault systems loaded by the same tectonic forces do not stay in remote areas. The Walker Lane runs through populated corridors. The Basin and Range Province underlies every major city in Nevada. The 1954 cluster is a demonstration of what the regional fault network can produce. And it happened on faults that had been quiet for long enough that most people in the region had no idea what was beneath them. Decades passed after 1954 without a repeat. That silence was not safety, it was accumulation. And what the ground did in 1954 that surprised everyone most was not the shaking itself. During the 1954 earthquake cluster in central Nevada, something happened that sounds physically impossible until you understand the mechanics behind it. Sections of the desert floor dropped, vertically, by up to 20 feet, in approximately 1 second. 20 feet is roughly the height of a 2-story house. Imagine standing on flat ground and in the span of a single heartbeat, the surface beneath you drops the equivalent of 2 full floors. The land on one side of a fault line stayed at its original elevation. The land on the other side fell away. Fence lines crossing the fault suddenly showed one post standing at normal height, while the adjacent post sat in a hole deep enough to bury a car. This kind of ground movement is called normal faulting, and it is the specific type of faulting that dominates in extensional zones like the Basin and Range Province. When the crust is being pulled apart horizontally, the rock does not just crack sideways. Blocks of crust drop vertically relative to their neighbours as the horizontal tension removes the lateral support. The fault plane itself is angled, so the dropping block slides downward along the angle of the fracture. The 1954 Dixie Valley earthquake produced a fault scarp, a visible step in the Earth's surface that extended for miles across the desert. Researchers who arrived to study it in the days and weeks following the event measured the vertical displacement at multiple points along the scarp. In the most dramatic sections, the ground had dropped between 15 and 20 feet. In other sections, the displacement was smaller, but still clearly visible as a sharp, fresh cliff cutting across the desert floor. Roads that crossed the fault were destroyed. A major highway crossing one of the rupture zones showed the asphalt on one side sitting far above the asphalt on the other, the gap between them too large to bridge by car. Infrastructure built across the fault line was simply torn apart by the movement. For modern Nevada, this type of faulting presents a specific engineering challenge. Buildings and infrastructure built across active normal faults face damage that shaking-resistant engineering cannot prevent. A building can be designed to sway without collapsing during strong shaking, but if the fault runs beneath its foundation and the ground on one side drops 15 feet while the other side stays put, no amount of structural engineering saves it. The building is physically torn in two. This is why geologists place such importance on identifying where active faults run beneath cities. A building set back from a fault, on ground that moves as a single unit during a rupture, can survive. A building directly over the fault cannot. Knowing where the fault is determines whether a structure stands or falls, regardless of how well it is built. The 1954 earthquake revealed fault segments in central Nevada that nobody had mapped beforehand. The ground simply broke along lines that existing surveys had not identified. That same scenario, a rupture along an unknown or poorly mapped fault, remains possible in populated Nevada today. And when the ground breaks along a fault that crosses a major road, the consequences extend far beyond structural damage. On May 15, 2020, a magnitude 6.5 earthquake struck the Monte Cristo Range in central Nevada. The epicenter sat in a remote area of Esmeralda County, a stretch of high desert with few permanent residents and no significant urban development nearby. By most measures, this was the kind of Nevada earthquake that generates scientific interest but limited news coverage. Remote location. Sparse population. Then geologists saw what the earthquake had done to United States Highway 95. Highway 95 is one of the most important roads in Nevada. It runs roughly the full length of the state, connecting Las Vegas in the south to Winnemucca in the north. Along the way, it passes through small towns, across open desert, and through terrain that has almost no alternate routes for hundreds of miles in any direction. It is a lifeline road, the kind of highway that ambulances, supply trucks, and emergency vehicles depend on to reach remote communities. The Monte Cristo earthquake tore open the road surface where the fault crossed beneath it. A visible crack ran across the highway. The pavement on one side had shifted relative to the pavement on the other. The road was impassable at the rupture point, forcing a closure that disrupted traffic across a wide region. The disruption highlighted a vulnerability that earthquake planners have been aware of for years. Nevada's road network is thin. Between major cities, the available routes are few, and many of them cross terrain where fault lines run close to or directly beneath the roadway. A major earthquake in a populated area would likely sever multiple routes simultaneously, cutting off communities and complicating emergency response at exactly the moment when emergency response is most critical. The Monte Cristo earthquake also produced other effects that extended beyond the road damage. A section of United States Highway 95 remained closed for days as crews assessed and began repairing the surface rupture. Water crossings in the area needed inspection. Remote communities that relied on that highway for supply deliveries had to find alternative arrangements. All of this happened from a magnitude 6.5 earthquake in a remote area with a small permanent population. Scale that scenario up to a magnitude 7 or greater in the Reno-Carson City corridor or the Las Vegas basin, and the road closure picture becomes dramatically more serious. Multiple major routes crossing known fault zones. Populations of hundreds of thousands cut off from hospitals, supplies, and emergency services. The infrastructure disruption becoming a secondary disaster layered on top of the building damage and casualties. The Monte Cristo earthquake also contributed something scientifically significant. It added to the evidence that Nevada's fault system is actively producing major earthquakes in the modern era. Combined with the Silver Spring sequence in 2026, the pattern shows a fault network under sustained stress that is breaking repeatedly across different areas of the state. Each major earthquake in the modern record tells geologists something new about where the stress concentrations are, how different faults interact, and where the next rupture might originate. But that knowledge is always incomplete, and there are faults beneath Nevada that remain completely invisible right up until the moment they break. The most dangerous fault is the one you do not know about. Known faults can be mapped, buildings can be set back from them, utilities can be designed to cross them with flexible connections, emergency planners can account for their likely behavior in a major rupture. Known faults are manageable risks. Unknown faults are ambushes. Nevada has an unknown fault problem that geologists describe as significant and growing. The same process that makes Nevada's valleys flat and livable also hides the faults that created those valleys. When a block of crust drops along a fault to form a valley, the low point of that valley begins collecting sediment. Rivers flow in from surrounding mountains. Ancient lakes fill the basin. Dust and debris accumulate over thousands of years. The result is a flat valley floor sitting on top of deep layers of loose material that completely buries the fault traces beneath it. The buried faults are called blind faults. They are real, they are active, and they are invisible from the surface. No surface expression hints at their presence. No ridgeline marks their trace. No visible scarp signals where they run. They sit beneath the sediment, loaded with stress, waiting for a threshold that nobody can identify because nobody can see the fault clearly enough to measure its state. Discovering blind faults requires drilling, seismic surveying, or waiting for them to rupture and reveal themselves. Drilling programs are expensive and can only sample small areas at a time. Seismic surveys, where researchers generate controlled vibrations and measure how they reflect off underground structures, can image buried fault planes but require significant resources and cover limited areas in a single survey. As a result, the geological maps of Nevada's valleys are incomplete by definition. They show the faults that have been found. They say nothing about the faults that have not been found yet. In some Nevada valleys, the known fault traces cover only a fraction of the likely actual fault network. The rest waits to be discovered, either by careful scientific work or by a sudden rupture that brings it to everyone's attention simultaneously. The Las Vegas Basin presents this problem in its most extreme form. The thick sediment beneath the valley, in some areas more than 1,000 feet deep, buries geological structures that surface mapping cannot reveal. Some of the faults crossing beneath the urban areas of Las Vegas are mapped with confidence. Others are estimated from limited data. And others are simply unknown, their existence inferred from the general tectonic framework, but their specific locations unknown. In 2019, a magnitude 7.1 earthquake struck near Ridgecrest, California, roughly 150 miles from Las Vegas. The earthquake was preceded the day before by a magnitude 6.4 foreshock. When geologists rushed to the area after the main shock, they found that the fault that ruptured was known, but had been considered less threatening than neighbouring faults. The rupture surprised researchers with its length and complexity. Parts of the fault system that broke had not been clearly identified in pre-earthquake surveys. If a major earthquake could reveal new fault complexity near Ridgecrest, it can do the same beneath Las Vegas or Reno. Every major earthquake teaches geologists something about the hidden architecture of the crust, usually at significant cost to the people living above it. And sometimes the danger comes not from the ground itself, but from the systems humans have installed beneath it. On a night in December 2025, thousands of phones across Nevada and California suddenly screamed. The emergency alert tone, the unmistakable sound that bypasses silent mode and blares from every device in range, fired simultaneously across a massive area. The alerts reported a magnitude 5.9 earthquake. Tens of thousands of people in cities across 2 states grabbed door frames, dove under desks, and covered their heads. The earthquake never happened. A technical failure in the earthquake early warning system issued an alert for a seismic event that did not exist. The alert was a false alarm, a phantom earthquake generated by a malfunction sent to millions of people's phones before anyone caught the error. The correction came minutes later, but by then the damage was done. People had fallen diving for cover. Shelves had been knocked over in the scramble, panic had spread through buildings, and in a few cases people had been hurt in the rush to take protective action. The incident exposed a vulnerability in the earthquake warning infrastructure that scientists and emergency managers had been working to improve for years. Earthquake early warning systems like the one operating across the western United States work by detecting the first faster seismic waves produced by an earthquake and sending an alert before the slower, more destructive waves arrive. The window of warning is measured in seconds, sometimes less than 10. But even a few seconds allows people to drop and take cover, allows trains to slow down, allows hospital operating rooms to pause critical procedures. When that system fires a false alarm, it creates its own casualties. People hurt in the panic response. Emergency services flooded with calls. Public trust in the system eroded, which means future real alerts may be ignored by people who remember the false one. The December 2025 false alarm in Nevada caused measurable harm despite being triggered by an earthquake that never occurred. The Western United States early warning system has improved dramatically since its initial launch. More sensors have been added to the network. Processing algorithms have been refined. The accuracy of real-time earthquake detection has increased. But the system still depends on a dense network of seismometers, and in parts of Nevada where the fault network is complex and the population is spread thin, sensor coverage remains less complete than in California. Gaps in sensor coverage mean that some Nevada earthquakes will generate less warning time than the system is capable of providing in better covered areas. A fault rupturing in an area between sensor stations may propagate significantly before the network detects it and sends an alert. By the time the alert fires, the most destructive waves may already be arriving. The false alarm of December 2025 became a case study for system engineers. Every failure in a warning system, whether a false positive or a missed detection, provides data that improves the next version of the technology. But those improvements take time, and the faults beneath Nevada are not waiting for better technology before deciding to move. There is also a question that goes beyond technology. Some of the factors that may be influencing earthquake activity in Nevada are not natural at all. Nevada's crust has been shaking under purely natural forces for millions of years. The tectonic stretching, the Walker Lane stress loading, the fault network grinding under planetary forces, all of it runs on a geological timescale that human activity has nothing to do with. But over the last century, humans have done things to the Nevada crust that some scientists believe may have altered earthquake patterns in localized areas. Nevada has a history of large-scale industrial activity that goes deep underground. Mining operations across the state have removed enormous quantities of rock from beneath the surface. The Nevada test site, operating from the 1950s through the 1990s, detonated over 900 nuclear devices underground, many of them with yields powerful enough to generate artificial earthquakes that registered on seismographs around the world. Geothermal energy operations across the state involve injecting water into hot rock at significant pressure and depth. Each of these activities alters the mechanical state of the rock in the area where they occur. Mining creates voids in rock that previously carried load, changing the stress distribution in surrounding material. Underground nuclear tests released enormous energy into the crust and potentially altered fault stress in the surrounding region. Geothermal injection operations are known in other contexts to trigger earthquakes, a phenomenon called induced seismicity, by increasing fluid pressure on fault planes and reducing the friction that keeps faults locked. Whether any of these activities have meaningfully altered earthquake patterns in Nevada is genuinely debated among researchers. The scientific consensus places the dominant driver of Nevada seismicity firmly in natural tectonic forces. The stretching crust, the Walker Lane loading, the basin and range dynamics. These processes generate far more total seismic energy than any human activity has added or subtracted. But localized effects remain a legitimate area of study. Some researchers argue that fluid injection from geothermal operations near certain Nevada fault zones may have contributed to the timing or frequency of small earthquakes in those specific areas. Others contend that the removal of rock through mining changes the local stress field in ways that can either promote or inhibit fault movement nearby. The nuclear testing question is more complex. Underground detonations at the Nevada test site generated significant ground motion at depth, and seismological records from the testing era show patterns that differ from purely natural seismicity. What long-term effects those detonations may have had on the mechanical state of the crust in central Nevada is difficult to isolate from the natural background seismicity that was occurring simultaneously. The honest answer is that scientists do not know with certainty. The natural tectonic forces driving Nevada's earthquakes are so large that separating a potential human contribution from the baseline noise is extremely difficult with current methods. The question remains open, studied but unresolved. What is resolved is that Nevada's natural fault system carries enough stored energy to produce major earthquakes entirely on its own, without any human contribution at all. And the question of how that energy moves from fault to fault and where it concentrates is one of the hardest problems in earthquake science. After the Silver Springs sequence in 2026, and with the memory of the August 2025 swarm near Valmy still fresh, scientists watching Nevada's seismic activity faced a question that their instruments could measure, but their models could not definitively answer. Are these swarms normal, or are they building towards something bigger? This is one of the most consequential and most difficult questions in earthquake science. Major earthquakes are often preceded by smaller earthquakes called foreshocks. The 1994 Northridge earthquake in California had foreshock activity in the days before the main event. The 2011 Tohoku earthquake in Japan was preceded by a significant foreshock just 2 days before the devastating magnitude 9 main shock. In both cases, the foreshocks were only recognized as foreshocks after the fact. The problem is that foreshocks look identical to regular earthquakes while they are happening. A magnitude 4.5 earthquake has the same characteristics whether it is a standalone event, an aftershock of a previous main shock, or a foreshock of a larger rupture that will occur next week. There is currently no reliable way to look at an earthquake in real time and determine which category it belongs to. Only the subsequent seismic history reveals the answer. When a swarm develops, scientists calculate probabilities. After the Silver Springs 5.7, researchers issued probability estimates for larger earthquakes in the following days and weeks. Those probabilities, based on established statistical models, indicated elevated but not extreme risk of a larger event. The sequence eventually wound down without producing a larger main shock. In hindsight, the 5.7 appears to have been the main event, but the Nevada fault system as a whole is not winding down. Multiple areas of the state showed elevated seismic activity in 2025 and 2026. Valmy in the north, Silver Springs near Carson City, small clusters in the central desert. Scientists tracking the statewide picture see a pattern of increased stress release across the Walker Lane system. Whether that increased activity represents a fault network approaching a larger breaking point, or simply reflects normal statistical variation in a highly active seismic zone, is the central debate. Some researchers argue the increased frequency of moderate earthquakes suggests fault segments approaching critical stress levels. Others point to historical records showing that Nevada goes through periods of elevated activity followed by quieter stretches, and that the recent activity falls within the range of normal variation. What both sides agree on is that the Walker Lane system carries enough total stored energy to produce a magnitude 7 or greater earthquake somewhere along its length, and that the recent activity has not released that energy. The swarms represent small payments on the geological debt. The principle remains. For the 2.5 million people living in Nevada's seismic zones, the distinction between warning and pressure release matters enormously in terms of when to act. But the preparation required for either scenario is identical. The question of which it is matters less than the question of whether the region is ready, and scientists have a clearer picture than ever of what a direct hit on a Nevada city would actually look like. Every earthquake changes the world around it. The fault that breaks releases its stored energy, but in doing so, it pushes stress outward into the surrounding rock. That stress does not spread evenly. It concentrates at the ends of the rupture and in specific geometrical zones around the fault plane. In those zones, the stress level in neighbouring faults increases. In other zones, it decreases. Scientists call this Coulomb stress transfer, named after the 18th century physicist whose work on friction and material failure laid the mathematical groundwork. The concept is straightforward in principle. When a fault moves, the rock around it adjusts. Some neighbouring faults end up closer to their failure threshold, others move slightly farther away. The geometry of the fault network determines which is which. This transfer mechanism explains patterns that previously puzzled seismologists. Why do earthquake sequences sometimes appear to march along a fault system, with each large event seeming to trigger the next one some distance away? Coulomb stress transfer provides the mechanism. The first earthquake pushes stress onto the next segment. That segment, already loaded by tectonic forces, reaches its limit faster than it would have without the added push. It breaks. Its rupture transfers stress to the next segment. The sequence continues until the chain reaches a fault segment that the stress transfer has actually destabilized from the opposite direction, reducing rather than increasing its loading. In the Walker Lane, this process plays out across a complex network of hundreds of fault segments, with varying orientations, depths, and mechanical properties. Researchers have modelled how stress moves through the Walker Lane system following major earthquakes using what they know about fault geometry from surface mapping and geophysical surveys. The models show clear pathways by which a major rupture in one part of the system could load fault segments many miles away, potentially within days or weeks. This connectivity is why geologists watch the entire Nevada fault network rather than individual faults. A major earthquake near Fallon does not just affect the immediate area. It sends a stress ripple through the Walker Lane that reaches other fault segments across the state. Some of those segments may be close to their own thresholds, needing only a small additional push from a distant earthquake to finally move. The 1954 earthquake cluster is the clearest historical demonstration of this mechanism in Nevada. The sequence of major earthquakes that occurred over several months, each on a different fault segment, shows stress transfer moving through the Basin and Range Province in a way that produced cascading failures. Modern seismologists can model that historical sequence using Coulomb stress transfer calculations and reproduce the progression of earthquake locations with reasonable accuracy. That ability to model historical sequences gives researchers some confidence in applying the same framework to current conditions. The Silver Spring sequence of 2026, the Valmy activity of 2025, and the longer historical record of Nevada seismicity all contribute data that scientists use to build a picture of where stress is currently concentrated in the Walker Lane system. The model they have built points towards several fault segments that have accumulated substantial stress over recent decades. Some of those segments run through areas that are very difficult to talk about in purely scientific terms, because the consequences of failure there involve real cities, real people, and a scale of destruction that numbers alone cannot capture. Seismologists have run the scenario thousands of times through computer models. A magnitude 7 earthquake striking a fault segment directly beneath or immediately adjacent to downtown Reno. The models vary in detail, but the broad picture they produce is consistent enough that researchers use a single term for what the output describes: a direct hit. The shaking begins within a fraction of a second of the fault rupturing. For people in the immediate area above the fault, there is no warning time. The early warning system may fire alerts for people farther away, giving them a few seconds to react. But directly above the rupture, the first wave arrives essentially simultaneously with the fault movement. The ground lurches. Buildings sway. Contents fly off shelves. For modern, code-compliant structures, this is the moment their engineering earns its keep. Steel-framed buildings flex. Concrete structures with modern reinforcement absorb the energy through design deformation. Elevators lock automatically. Some damage occurs, but well-built modern structures are designed to stay standing through a magnitude 7 event, even with significant internal damage. The older structures fail differently. Unreinforced masonry buildings, the brick and block structures built before modern seismic codes became standard in Nevada, do not flex. Brick is rigid and heavy. When it shakes violently, the mortar between bricks cracks. Walls separate from floors. In severe cases, the entire facade of a building peels away from the structure and falls into the street. Collapses concentrate in older residential neighborhoods, in the historic commercial district, and in any buildings added to the National Register of Historic Places without seismic upgrades. Beneath the city, utility systems fail. Water mains crossing the fault rupture at the displacement point. Pressure throughout the water system drops suddenly. Fire hydrants become unreliable across entire districts. Gas lines crossing the fault break, releasing gas that can accumulate in basements and damaged structures. Electrical systems short out at multiple points simultaneously. The power grid in the affected area may go dark within seconds. Traffic signals fail across the city. Roads directly over fault traces crack and shift, blocking emergency vehicle routes. The main bridges crossing the Truckee River, which flows through central Reno, need immediate structural inspection before being cleared for heavy vehicles. Interstate 80, the primary east-west highway connecting Reno to California and the rest of Nevada, crosses fault zones that a direct hit would damage, potentially closing the highway to truck traffic. Hospitals in Reno are the next critical variable. The city has trauma centers capable of handling a major mass casualty event under normal circumstances. A major earthquake simultaneously generates hundreds or thousands of casualties while also damaging the hospital buildings and their utility connections. Surgeons cannot operate without stable power. emergency rooms cannot function with compromised water supplies. The demand for emergency medical care spikes at the exact moment the capacity to provide it drops. Emergency planners estimate that a major earthquake in the Reno corridor would require mutual aid from across the region. Resources from California, Utah, and federal stockpiles would need to move into Nevada within hours. The roads to bring them in would be partially compromised. The airports would need rapid assessment before large cargo aircraft could land. The first 72 hours would be defined by simultaneous crises, competing for resources that simply do not exist in sufficient quantities on the local level. Nevada has been planning for this. But plans and reality meet in uncomfortable ways when the ground finally moves. Statistics do not predict earthquakes. No equation tells you the exact date and time a fault will break, but statistics do tell you something important about risk accumulation. And the numbers for Nevada tell a story that demands attention. Nevada averages a magnitude 6 or greater earthquake roughly once every 10 years, a magnitude 7 or greater roughly once every 27 years. These averages come from analysing the historical record of large earthquakes in the state, going back over a century of instrumental recording and further into the geological record through fault trenching and landscape analysis. The last magnitude 7 or greater earthquake to strike Nevada was the Monte Cristo event in 2020. A magnitude 6.5, large, destructive, but on the lower end of the 7+ category. Before that, the last truly major Nevada earthquake occurred in 1954, when the Dixie Valley and Fairview Peak earthquakes struck the Central Desert. Between 1954 and 2020, Nevada went 66 years without a magnitude 7 or greater earthquake. The statistical average suggests one should occur every 27 years. 66 years represents more than 2 full average cycles without the expected event. During those 66 years, stress continued loading onto faults throughout the Walker Lane and the Basin and Range province. The energy that statistical averages suggest should have been released in 2 or 3 major earthquakes was instead stored in rock. Statistical averages in earthquake science are not the same as clocks. A fault does not reset to 0 after an earthquake and begin counting toward a fixed future date. The system is more complex. But the principle of stress accumulation is real and measurable. Faults that have not ruptured in longer than their average interval carry more stored energy than faults that have recently released. The longer the quiet period, the more loaded the system becomes. The Walker Lane currently holds stress accumulated over decades. The major fault segments closest to populated areas have not produced magnitude 7 events in living memory for most Nevada residents. The geological record shows they have produced such events in the past and will produce them in the future. The gap between the last major rupture and today represents energy that the system has absorbed without releasing. Scientists calculate annualized earthquake loss figures for Nevada to put the cumulative risk into economic terms. These figures estimate how much damage, on average, earthquakes cause in the state per year when averaged over long periods. For Nevada, this figure runs into the tens of millions of dollars annually, even without a major urban earthquake. A single magnitude 7 event centered near Reno or Las Vegas would generate losses that exceed the cumulative annual average many times over in a single day. The math of when is uncomfortable precisely because it cannot give a specific answer. The closest it can offer is this: a state that historically produces major earthquakes on a regular cycle. A fault system under sustained and growing stress. A population of 2.5 million people living in the highest risk zones, and a quiet period that has extended longer than the statistical average would predict. The next chapter in Nevada's seismic history is not a question of possibility, it is a question of scale. Earthquake early warning systems are one of the genuine success stories of modern seismology. Japan has the most advanced system in the world. When a major earthquake strikes offshore, sensors detect the initial fast waves and send alerts across the country within seconds. Train networks slow automatically. Hospital procedures pause. Millions of people get a warning before the damaging waves arrive. The system has saved lives in multiple major earthquakes since it became operational. The Western United States runs a similar system called Shake Alert. Sensors across California, Oregon, and Washington detect earthquakes and send automated alerts to phones, emergency systems, and critical infrastructure. Nevada is integrated into this network, though sensor coverage across the state is less dense than in California. The fundamental limitation of any early warning system is physics. The fast waves that sensors detect travel at roughly 3 to 4 miles per second. Alert systems require time to detect those waves, confirm they represent a real earthquake, calculate the expected shaking, and send the notification. Even with the fastest systems, people directly above an earthquake epicenter receive no warning. The shaking arrives before any alert can be sent. The warning window grows with distance from the epicenter. Someone 10 miles from the rupture might get 5 seconds of warning. Someone 50 miles away might get 30 seconds. Someone 100 miles away might get a minute or more. Those differences in warning time determine what people can actually do with the alert. 5 seconds is enough to drop and take cover. 30 seconds allows more meaningful protective action. A minute allows hospitals to pause surgeries and factories to stop dangerous processes. The geometry of fault locations relative to city centres, therefore, determines how much warning time residents actually receive. For Reno, with fault lines running directly beneath the city, warning times for the most likely earthquake scenarios are extremely short. The fault and the population centre are in the same place. The shaking and the warning arrive almost simultaneously. The people who benefit most from the warning system in a Reno earthquake scenario are those in communities farther away, places like Sacramento or the Lake Tahoe region, where the extra distance provides life-saving seconds. Nevada has been expanding its seismic monitoring network. Additional sensors installed in recent years improve both warning time and the accuracy of the system's earthquake characterization. Better sensors mean faster and more reliable alerts and fewer false alarms, like the December 2025 incident. The work continues, driven by geologists who understand what the fault network beneath their state is capable of producing. Construction science is also advancing. Building codes in Nevada have been updated repeatedly to incorporate lessons from major earthquakes worldwide. Engineers have developed materials and structural systems that perform dramatically better during strong shaking than older construction. Seismic retrofitting programs, where older buildings are upgraded to meet modern standards, have made progress in some areas. But the inventory of vulnerable older buildings across Nevada cities remains large. The resources required to retrofit every at-risk structure across Reno, Carson City, and Las Vegas would be substantial. Progress is real and ongoing. The gap between the current state of the building stock and full seismic preparedness remains significant. Science and geology are in a race. The outcome depends on which moves faster, the improvements in warning systems, building standards, and emergency planning, or the fault system beneath 2.5 million people reaching its next breaking point. Hoover Dam sits on the Colorado River at the Nevada-Arizona border, roughly 30 miles southeast of Las Vegas. It is one of the most important pieces of infrastructure in the American West. The dam holds back Lake Mead, the largest reservoir by volume in the United States, when at full capacity. It generates hydroelectric power for Nevada, Arizona, and California. It regulates the flow of the Colorado River, which provides drinking water and irrigation water to tens of millions of people across the Southwest. The Hoover Dam was built with seismic considerations in mind. Engineers designing it in the 1930s understood that the canyon it sits in is geologically active. The dam's arch design is inherently resistant to seismic loading, and the concrete structure is performed without significant seismic damage through every earthquake the region has experienced since construction. The dam itself is generally considered robust against the expected seismic hazard. The more vulnerable elements are the systems connected to it. Transmission lines carrying power from Hoover Dam to Las Vegas, Phoenix, and Los Angeles follow routes across terrain that crosses active fault zones. A major earthquake near Las Vegas could damage or destroy critical sections of these transmission corridors, cutting off power to the Las Vegas Valley while leaving the dam itself intact. The power would be generating but unable to reach the people who need it. The water delivery system is equally complex and vulnerable. The Southern Nevada Water Authority draws water from Lake Mead through intake structures and delivers it through a network of pipes and treatment facilities to the Las Vegas Valley. Some of those pipes run across or near fault zones in the Las Vegas Basin. A major earthquake causing fault displacement beneath water infrastructure could rupture delivery lines, contaminating or cutting off the water supply to the Las Vegas metropolitan area. Las Vegas has no significant local surface water supply independent of the Colorado River system. The groundwater beneath the Las Vegas Valley has been substantially depleted over decades of rapid population growth. The city depends on the Mead delivery system in a way that makes it uniquely vulnerable to any disruption in that infrastructure. In 2021, drought conditions dropped Lake Mead to historically low levels. The experience forced Las Vegas to confront its water supply vulnerability in a new way and accelerated conservation programs and alternative sourcing initiatives. An earthquake disrupting the delivery infrastructure would create a water emergency on top of a structural emergency, compounding the demands on emergency management resources. Emergency planners model these scenarios. The calculations show that Las Vegas has limited capacity to store emergency water reserves within the city, relying instead on continuous delivery from an external source. The contingency plans for a major water supply disruption involve trucking in water, drilling emergency wells, and imposing severe conservation measures across the metro area. A seismic event large enough to damage the water delivery network would trigger all of these contingency measures simultaneously, at a moment when the city is also dealing with building damage, medical emergencies, road closures, and power disruptions. The interdependence of modern urban infrastructure means that a single major earthquake becomes multiple simultaneous crises. The Colorado River is already the most contested and stressed water system in the American West. A major southern Nevada earthquake would add seismic damage to the list of pressures that system already faces. Everything described in the previous 31 chapters happens on a human timescale. Days, years, decades, centuries at most. The earthquake risk to Nevada's cities is present, real, and measured in probabilities that apply to people alive today. But the Walker Lane fault system is also operating on a geological timescale that makes even human civilization look like a brief moment. And on that longer timescale, the Walker Lane is doing something extraordinary. Geologists studying the rate at which the Walker Lane absorbs tectonic motion, and the rate at which that absorption has been increasing over geological history, have projected the trend forward. The math produces a conclusion that sounds impossible until you understand the mechanism behind it. Over the next 7 to 8 million years, the Walker Lane is expected to progressively take over as the primary boundary between the Pacific and North American tectonic plates. The San Andreas Fault, currently the main plate boundary running through California, will gradually become less active as more of the tectonic motion shifts eastward into the Walker Lane. The center of plate boundary activity will migrate from coastal California into Nevada. As the Walker Lane becomes the primary plate boundary, the zone between the old San Andreas and the new Walker Lane boundary, essentially the entire western strip of California, will increasingly move as part of the Pacific plate rather than the North American plate. Los Angeles. San Diego. The Mojave Desert, the Central Valley. All of this terrain will gradually separate from the continental mass. The trough created by the Walker Lane, the long zone of extensional faulting that is already a geographic low point in many areas, will eventually sit at or below sea level along much of its length. Ocean water will flood in from the south, filling the trough the way water fills a ditch. Over millions of years, what is now the Nevada-California border region will become a new arm of the Pacific Ocean. California will become an island. The Baja California Peninsula, which is already separating from mainland Mexico along the same general tectonic system, previews this process. Baja is currently being pulled away from the Mexican mainland by tectonic forces that parallel what the Walker Lane is doing further north. The gap between Baja and the mainland has been growing for millions of years. The gap between California and the rest of North America will begin a similar process. On a 7 million year timescale, Nevada will have an ocean coastline to its west. The mountains that currently define the California border will be islands. The state that is now landlocked desert will border a sea. This is not speculation dressed up as science. It is the projection of documented, measured, ongoing tectonic processes carried forward in time using the same physics that governs the movement of plates today. The rate of tectonic transfer from the San Andreas to the Walker Lane is measurable. The geometry of the future plate boundary is predictable from current fault orientations. The flooding of the Walker Lane trough follows directly from the topography that the faulting is already creating. 7 million years is beyond any human frame of reference, but the forces driving that future are the same forces loading Nevada's faults right now. The same energy that will eventually reshape the western continent is the energy sitting in the rock beneath Reno and Las Vegas today. And for the 2.5 million people living above it, the long-term geology is less important than the short-term reality. 2.5 million people. That is the population living in Nevada's highest risk seismic zones. Reno, Las Vegas. Carson City. Sparks, Henderson, Summerlin, communities built over decades on valley floors created by the very fault systems that still threaten them. They live in homes built on sediment that amplifies shaking. They drive on roads that cross active fault traces. They drink water delivered through pipes that run near fault zones. They work in buildings of varying ages and varying resilience. And the vast majority of them go through each day without thinking about the ground beneath their feet, because the ground has not moved dramatically in their lifetime. That silence is not safety. It is accumulation. Every chapter in this story has pointed toward the same place: a fault system under growing stress, a Walker Lane absorbing increasing tectonic energy as the San Andreas geometry becomes more resistant, multiple populated corridors sitting directly on active faults, a geological history filled with magnitude 7 events that struck with no meaningful warning and reshaped the landscape in seconds, a recent record of escalating seismic activity, from the Valmy Swarm in 2025 to the Silver Spring sequence in 2026, suggesting a fault network closer to its limits than it has been in decades. The question that science cannot fully answer is not whether Nevada will experience a major earthquake. Nevada has always experienced major earthquakes, and always will. The question is where and when the next magnitude 7 or greater rupture will occur, which city sits closest to the epicenter, and how much of the stored tectonic energy the next major event will release in a single rupture versus distributing it across a sequence of smaller ones. Geologists can narrow the probabilities. They can identify the highest risk fault segments, calculate the most likely magnitude ranges, and model the expected ground motion patterns for different rupture scenarios. They cannot collapse those probabilities to a single date and location. The physics of fault failure remains partly unpredictable at the level of precision that would allow a specific warning. What science can do, and what geologists and emergency managers across Nevada are doing, is use the incomplete but substantial knowledge they have to reduce casualties and economic loss when the next major event does occur. Better building codes. Seismic retrofitting of the most vulnerable structures. Dense sensor networks providing the maximum possible warning time. Emergency response plans that account for simultaneous infrastructure failures. Public education that turns awareness into preparedness. A person who knows to drop and cover when shaking begins. A family with water and supplies stored for 72 hours. A neighbourhood whose older buildings have been retrofitted. A city whose hospitals have backup power and flexible utility connections. These things do not prevent earthquakes. They reduce what earthquakes do to people. The Walker Lane is going to keep loading. The Basilan Range province is going to keep stretching. Nevada is going to keep growing 2 acres per year, each acre representing another small increment of stored tectonic debt. The faults beneath Reno and Las Vegas are going to keep accumulating the energy that planetary forces have been building for 20 million years. The only variable that humans control is how ready they are when the debt finally comes due.